Over the years, humans have come to understand, well, the four fundamental forces of our universe. Like gravitational force, the electric force plays an important role in our everyday life. With the help of the electric force, we are able to generate and use electricity, which is essential for us in our modern age. So what is electricity? How does it work? What is the difference between current and voltage? We already know that everything is made up of atoms. Atoms are very, very tiny. A copper penny would have nearly 3.2 into 10 to the power of 22 copper atoms inside. However, even the atoms aren't small enough to explain the workings of electricity. We need to dive deeper to the center of the atom. Here, the center is called the nucleus. It is made up of particles called protons and neutrons. Nuclei contain one or more protons and usually an equal number of neutrons. There are also electrons in orbit around the nucleus. Protons have a positive charge, electrons have a negative charge, while neutrons have no charge. The number of protons determines the kind of atom or element. For example, if an atom contains 1 proton, then it's hydrogen. If it has 6 protons, then it's a carbon atom. The number of protons is called the atomic number of an atom. In a stable atom, the number of electrons is equal to the number of protons. So their charges cancel each other out and result in the atom becoming neutral and stable. If the number of protons is greater than the number of electrons, the atom is called a positively charged atom. Similarly, if the number of electrons is greater than the number of protons, the atom is called a negatively charged atom. We call both positively and negatively charged atoms ionized atoms, because the same charges repel each other and opposite charges attract each other. Negatively charged electrons orbit positively charged protons. Electrons orbit the nucleus, but at different energy levels, also known as shells. The shell closest to the nucleus can hold 2 electrons. The next shell can hold up to 8 electrons, and outer shells can hold even more. The amount of force acting on 2 charges depends on how far they are from each other. The closer 2 charges get, the greater the force becomes. The electrons in the shells closest to the nucleus have a strong force of attraction to the protons in the center, but the electrons in the outermost shell can't easily hold their position due to the distance from the center. These electrons are called valence electrons. These valence electrons can be easily pushed out of their shell when enough force is applied. This is how electrons jump from one atom to another. These moving electrons are what we call electricity. Atoms sharing their electrons between one another create electricity. In simple terms, moving charged particles creates electricity. That means electrons have an electric field, and when electrons move, electricity is created. If we look at the copper atom, it has 1 valence electron. And if we look at the silver atom, it also has a valence electron. So from these atoms, we can easily remove electrons with enough force. These materials are called conductors. Most of the metals are conductors, but some materials hold their electrons very tightly, and they don't share their electrons with nearby atoms. Those are called insulators. Insulators serve a very important purpose. They prevent the flow of electrons. For example, plastic, rubber, and glass are made up of these types of atoms. How can we move electrons from one place to another? It is not a complicated thing. When we rub 2 objects, electrons will be transferred from one to another. In some cases, you don't even need to rub 2 objects. Sometimes even simpler contact between 2 different materials is enough to transfer electrons. For example, when you walk across the carpet, electrons transfer from your body to the carpet. As a result, you have an absence of electrons in your body. Nature is always trying to maintain a stable state, so your body then looks to find electrons. Carpet is a good insulator, so you can't get electrons from that. But when you touch a metal, your body gains electrons from the metal. In that scenario, you feel a little shock in your hand, because electrons moving to your hand from the metal create electricity. Now we look into a simple electric circuit with a battery. Here the battery is an external force. It acts like a pump. One side of the battery has an excess of electrons and the other side does not. Inside the battery, an insulator facilitates the separation of electrons through chemical reactions. So here, electrons from the battery move through nearby atoms. Those nearby atoms should contain valence electrons. As we have seen before, copper atoms are good conductors, which contain valence electrons. So we normally use copper wires as a conductor. Electrons come from the battery, pushing the copper atom's electrons. So electrons flowing in the wire in the same general direction create electricity. The movement of electrons from atom to atom is the same everywhere along a wire. The distribution does not change as the electrons move. When you disconnect the battery, each atom is left with its proper number of electrons. The number of electrons that came out of the wire at the negative terminal is exactly equal to the number that entered the wire at the positive terminal. Only electrons can move if their circuit is closed. If it's open, electrons can't move, and so no electricity. If we place a light bulb between the closed circuit, the bulb starts glowing. But how does it glow? Normally, a bulb has a thin filament made of tungsten. Even though tungsten is a conductor, it has some resistance. The long, thin, twisting path creates an electric resistance and affects the flow of electrons, so the electrons cannot freely move between atoms. Atoms in the tungsten start vibrating, heating up the tungsten, and as a result, it begins to provide light and glow. We heard the word current. So what is electric current? A simple small copper wire contains trillions and trillions of electrons. In a complete closed circuit, electrons moving from one to another direction. If we look at a single point, we can calculate the number of electrons passing through this point per second. Current is measured in amperes. 1 ampere is equal to 1 coulomb. The rate that electrons move through a conductor is beyond the ability of the human mind to imagine. 1 coulomb of electrons means 6.28 billion electrons, or 6.28 into 10 to the power of 18 electrons, flowing past a given point in 1 second. So the 1 ampere is the number of electrons passing through a point in 1 second. It means the number of electrons that pass a given point in this conductor in just 1 billionth of a second is greater than the total number of people living on Earth today. This calculation is similar to the flow of water. We can calculate how many liters of water pass through a particular point in 1 minute. So electric current means nothing but flow. It is the rate at which electrons flow past a point in a complete electric circuit. Now we understand how electrons can flow, but how do we get them flowing in the first place? That's what batteries or generators do. They push the first electrons. That push is called voltage. In a battery, one end has an excess of electrons, while all of the positive charges are on the other side. So there is an energy difference between 2 points called the electric potential difference. So what exactly is the electric potential difference? Let's consider a motionless ball on the surface of the Earth. This ball is at rest, so its potential energy is 0. If we want to move the ball directly upward, we need to provide some energy against the gravitational force acting to pull the ball down to Earth, because gravity is always pulling objects on Earth down. So, we provide some energy to push the ball up into the air, and the ball will get some potential energy. So the ball above the surface has high potential energy, considering it has 5 joules. So we calculate the difference between the two balls' potential energy. The potential difference will be 5 joules. This is called gravitational potential difference. Now we come to electric potential. Similar to gravitational potential, there is electric potential energy between 2 charged particles. In terms of gravity, 2 objects always attract each other. But in terms of electric force, equally charged particles repel each other, and oppositely charged particles attract each other. So here, positive and negative charged particles stick together due to the electric force. Now we need to do some work against the electric force to move the negative particle away from the positive particle. For any charge located in an electric field, Its electric potential energy depends on the type of charge, amount of charge, and its position in the field. So here, consider the potential energy of one end is 2, which is in its lowest potential state, and the other end has a high potential state of 3.5. So the potential difference between 2 points is 1.5 joules per coulomb, or simply 1.5 volts. So charges are always trying to equal the potential energy difference. In a 1.5 volt battery, the electric potential difference between 2 points is 1.5. When we connect a copper wire to a battery, because of electric potential difference, electrons are pushed by the negative terminal and pulled by the positive terminal. The electrons in the copper will move from one atom to atom, creating a flow of charge we know as electricity. The battery will dry out when the potential difference between 2 points becomes 0. The flow of electric current is dependent on voltage. This means that increasing the voltage will cause the current to increase. The less voltage, the less current. The more voltage, the more current. If we connect a 100-volt battery in a simple small wire, the push of the electrons is very high. The atoms inside the wire are not able to carry the flow of so many electrons, so atoms start vibrating. The wire will heat up, causing damage or fire. That's why we use wire with the appropriate thickness, depending on voltage. Even though we humans are well trained about how to handle electric force on a global level, more than 1.2 million electrical-related accidents occur every year. So we need to be more careful to handle the universal forces. And if we use these forces properly, the time is not too far when we humans will become an advanced civilization in this universe.